Okay, let's look at some more examples, more review. Let's talk about domain. It's a big topic in any math class. We basically had, we had a log function with domain restrictions. We had a root function with domain restrictions. We had polynomial functions. And we had rational functions. Okay, start with the easy one. Domain, all real numbers, right? For any polynomial function, no issues there, so we're good. Square root function, you know that you have to take the square root of a non-negative value. So I would set up this inequality right away, and then I'd solve it. All right, so the idea is that whatever's under there is non-negative, and then solve the inequality. And I just made a mistake. Whenever you divide by negative, if that happens, you got to flip your sign around. So you should get the following set. And I'm okay with this as an answer. My math lab always liked this answer. Either one is okay with me. All right, and that's how you deal with radicals. This one's pretty similar to this, but you can't take the natural log of 0. So you'd have to take whatever's in your natural log and set it just greater than 0, not greater than or equal to. And then interval notation, -1 to infinity, not included. And of course, our rational function, we can't divide by 0. So that means I have to, in this case, take the denominator. We had a whole section on these, so you can do a lot more with rational asymptotes, horizontal asymptotes, vertical asymptotes, intercepts. But for the domain, we would just set the numerator to 0. You could factor or solve by taking roots, and you get -1 and 1. And those are excluded, right? We say x cannot be those. We wanted to use this notation. X cannot be -1 and 1. Okay, while we're talking about logs, I had a log problem, domain problem. Let's look at some equations. So basically, what do we do with logs? I said something like that. And again, this is no calculator. I can give you an exponential equation. All right, how do you solve these? Let's start with the log. We use our properties if we have to. In this case, the difference of two logs would be the log of the quotient. And then this is the special property here. We go base to power equals what you're taking the log of. So it would be e to the second equals x minus 1 over 5. And then from here, it's an algebra problem. Multiply both sides by 5. And get used to these weird answers, especially if you can't use a calculator. You add 5 to both sides. It's the same algebra. Your answer just isn't a decimal. I get 5e squared plus 5. Okay, the key step is this step. When you say e to the 2 equals that. Exponential, first I would isolate my exponential piece. And then you're going to take the log of both sides. It'd be your choice. I usually do the natural log. You could do log base 2. And I use my properties. The natural log of an exponential, the exponential piece comes down. You're left with the natural log of the base. And that equals the natural log of what you took, the right-hand side, 8/5. And now I'm trying to solve for x, right? So I would divide by ln2. And now I have x minus 1. And my last step would be to add 1. And I'm out of space over here, but add 1. And x equals this guy. ln 8/5 divided by ln2 plus 1. No calculator needed. Let's see. We did the vectors. A brief review of the vectors. There's also don't forget word problems for vectors. Breaking your force vector into horizontal, vertical components. We got the compound interest. Now this one's hard to do without a calculator, but I can still kind of ask you to set something up. For example, you have $2 compounded A, B, I could say, I don't know, quarterly, compounded continuously, and for 5 years, something like that. So you'd set up your equation. I'd have to give you your rate, right? So you got your two formulas. So your amount, if it's continuous, would be your $2 e to the r t. That's your function. And if it's 5 years, you just plug 5 in. Remember, I could also give you the amount. How long before you have $100? You'd have to put 100 in here and then solve. You can do that without a calculator. I mean, you might not be able to do the final step, but you couldn't do some of that without a calculator. The other function would be, if it's quarterly, you use your initial amount, 1 plus the rate, over the number of times it's compounded, and then to that number times t. So that's how you build your functions. And then from there, you can answer any questions about your functions. Okay, what else we got here? I have a note to myself, sine of a plus b. That means, oh, this one, a lot of people got this one wrong. I remember this one. What if I say the sine of a is 4/5 and the cosine, go away equation. Okay. And I said the cosine of b is -1/3. And I want you to find for me the sine of a minus b. And I could ask you all kinds of stuff. Cosine a plus b, sine a plus b, tangent of a over b. Sorry, not a over b. The tangent of a over 2, the tangent of 2a, right? All those formulas that you have for sum of two angles, double angles, and half angles. So I'll just do one of them because they all work the same. When I say they all work the same, if I ask you for the sine of a minus b, you go sine a, sine b. No, sorry. Sine a cosine b minus sine b cosine a. That's the formula I look up. Okay, and that means there's going to be 4 fractions. And some of them are given, right? Cosine b, that's -1/3. Sine a, that's 4/5. But I still have to find these two. All right, and I have to give you more information because sine's positive in 2 quadrants, cosine's negative in 2 quadrants. So I might say a is in quadrant 2. And I might say b is in quadrant 3. Okay, so you'd have to do 2 kind of basic trig problems to find these guys. That would be finding sine of b. So I draw a picture for b. If it's in quadrant 3, it has -1/3. That's adjacent over hypotenuse. 9 minus 1 is 8. This would be 2√2 negative. Pythagorean theorem. So that means the sine of b, if this is b, is -2√2 over 3. Cosine a, same thing. I draw a picture of a. It's in quadrant 2. It has a sine value of 4/5. Pythagorean theorem. That should be -3. So the cosine of a is -3/5. X over r. All right, and then from here I go 4 over -15. 4 times 4 over 15, negative. And then here I got 1, 2, 3, negative, so it's going to be a negative. And this would be what? 6√2 over 15. And that's my answer. You could write that as a single fraction. It would look a little bit better. like this, -4 minus 6 root 2 over 15. Make sure you look at those ones, because that was a problem on test, I think it was test 2. A lot of people missed that one. All right, I got 2 more topics. Solve triangles. So with or without a word problem, you get something like this. And you can solve that triangle, right? Whether it's in a word problem or not. You could use a trig function to find one of the other sides, for example. Call that, I'd call it y. All right, and you can solve that because you know, without a calculator, if I give you a special angle, right? Because you know that the tangent of 45 degrees is 1. In addition to that, you got your non-obliques, or your non-right, and we got law of sines and law of cosines. So now remember, without a calculator, it's hard for me to make you do all of this. So if you remember the last test, I said, well, how would you solve it? And maybe you give me a little bit of info on how to solve this using either, depending on what's given, you got your law of sines, or I could ask you just to set it up, law of cosines. Okay, so that's without doing an example, that's solving right triangles and oblique triangles. Okay, and then doing pretty good. Conics. Let me do one conic. I'll do one difficult conic, and that means I'll kind of talk about the other ones as I go through it. So if I give you this, if you can do the tough one, you can do the easy one. So I say, go ahead and graph this for me. Okay, identify what kind of conic it is and graph it. So remember, you got 3 choices: ellipse, parabola, hyperbola. There's also circle, but we don't do those in here. And this would involve completing the square. So I'm going to group my x terms. Group my y terms. And get rid of the other thing. This one's looking familiar. I guess there's not a whole lot of variety I can give you if I want to give you a nice, if your answer wants to come out nice and neat, that is, everything's a perfect square. So let's see what happens. I'm going to factor out the 4. I'm going to factor out the 9. And over here I got a -144. Now I'm going to complete the square. Half of that, square it. Half of this, square it. And then I got to add these to both sides. But remember, I'm not adding 36 to both sides. I'm adding 36 times 4 to this side. I think that's 144, right? And then I'm not adding 16 to both sides. I know I added it here, so I have to add it over here. But it's really 9 times 16, right? So you got to be careful not to add 16 to both sides. But if you factored something out, I'm adding 9 times 16, which is also 144. Okay, so those go away. I should be left with just 144 on the right. And then I can factor these because I created 2 perfect squares. And then I divide everything by 144 to get this equal to 1. Right? And I go from there, right? I should be able to write everything over. And like I said, that's why these ones they seem kind of repetitive, because if I want this to reduce to have a nice denominator, which in this case would be 16, and in this case 144 divided by 4, which we already did, we multiplied it, 36. And now I got my nice, neat form of a conic section. And that's an ellipse, right? So we know it's